Okay. No one has still joined. It's already full. You can wait for a few minutes. Then we will start. Okay, so Mohan has joined. Okay, let me share my screen. So if anybody watches, because I will anyway record the video and then I'll upload it on YouTube and I'll share the YouTube link in the spreadsheet. So you can follow up by watching that recorded video. And if anybody joins in between, then obviously we'll follow. Now let me start by sharing my screen. Oh, so let me share my screen now. Okay. I think it is visible. I don't know how to check it, but I think so. I hope so. It's visible. Yeah. Okay. So, yeah, great. So let me start. So in this class, basically, we'll solve numerical exercise, numerical problems based on the lectures uploaded in this week. So it's not very difficult to catch up. You can catch up from online also, yeah, from YouTube video that I will upload. Okay. So let me start. Okay. So what will be our question number? Sorry, question number one. So let me find out relevant questions to begin with. Yeah. Is Sunday? Not wrong. Yes, it's okay. So the change in entropy when 2 moles of argon gas are heated at constant volume from 300 Kelvin to 500 Kelvin. So you have to find out the change in entropy uh, for 2 moles of argon gas, and which is heated constant volume from 300 Kelvin 500 Kelvin. So this is our problem. So how you can solve it? So for that you have to remind that formulas which is associated with the entropy change. That was del S was equals to CV ln T2 by T1 minus NR ln V2 by V1. So this is the formula, but here you can see that volume is constant, that is a constant volume process, and 2 moles of argon gas are heated. Just we are heating 2 moles of argon gas. There are, let's say this is a container, here 2 mole of argon gas are there, 2 mole of argon gas, and we are just heating. This is our procedure, and we are increasing the temperature by heating from 300 Kelvin to 500 Kelvin. So you know there are three variables. Any properties, any state functions can be represented with three variables, which are pressure, volume, and temperature. Okay, so here it's clear that now temperature and pressure, the temperature is changing, volume is fixed, and obviously here is no mention of pressure, so you can consider the pressure is also fixed. Okay, so easily from here it can be reduced, that formula, that CV ln T2 by V1, because this part will anyway vanishes because V2 equals to V1. Okay, now if you calculate it, we are considering this is a constant pressure process, because this type of uh, heating usually performed under constant atmospheric pressure, which is 1 atm. So this is CV ln T2 by T1. Now if you just calculate it, what is CV? CV is not given, so we have to calculate CV. You know CV, how you can calculate CV? CV is for ideal gas, obviously for ideal gas, it is del U del T V. Now for monoatomic ideal gas, argon is a monoatomic ideal gas. For monoatomic ideal gas from equipartition theory, you know that for 1 mole of monoatomic ideal gas, U is 3 by 2 RT. Then CV will be essentially 3 by 2 R. That value we can use. So this is then 3 by 2 R ln, and T2 by T1, that is explicitly given here. So T2 is 500 and T1 is 300. So if you put it, then we'll obtain 1.5 R ln 5 by 3. This will be our answer. Now, the total unit, because this is a number, this is a number, so total unit will be guided by this R, universal gas constant. So we can write it as ln 5 by 3. This will value into R. In joule, you know, 8.314 joule per Kelvin per mole inverse. Sorry, joule mole per Kelvin. Okay, so this will be our unit. So now you have to calculate it. So let me calculate. What will the answer? It is ln 5 by 3. So ln 5 by 3 is eventually, this is 1.5 into, it is 0.510 into 8.314 joule mole Kelvin inverse. So it will be essentially into 8.314. So it is okay. There is one catch. Okay, here is 2 moles of argon gas are there. Okay, sorry. So 2 moles of argon gas are there. So basically there will be CV will be now 2, because this is for 1 mole. For 1 mole, obviously, because R is there. So this is for 1 mole. So basically you have to write it for CVM, not CV. So then CVM is C by R, but here we have to calculate it for 2 moles. So CV can be written as NCVM, this you know, NCVM. So in general, you can write it NCVM. So if you write it NCVM, then you have to multiply it with the number of moles. So essentially, then it will be 3 because there are only 2 moles. N is 2. N equals to 2 moles. So then it will be, everything will be multiplied by 3. Okay. So then answer should be our, yes. So answer, what will be the answer? NR 92 by 2 1, everything is perfect. Okay. Log 5 by 3 is also okay. So it is 12.7410 joule mole Kelvin inverse. So this will be our change in entropy. And you know, if the change in entropy is positive, entropy change, that means it is spontaneous. Okay. So this is the first question. Now going to the second question. Question number 2. Okay, just let me check whether everything is going okay or not. Mm, okay, recording is also perfectly going on. And somebody joined and then left, so okay, it's okay. Oh, it's disconnected. Let me reconnect it. Oh, this is just laser new features. Okay. So now question number 2. Oh, sorry. Now again we have to consider the process for the process. What is the process that is mentioned here in the question? That is 1 mole of argon gas from 300 Kelvin and 1 bar. Now here you can see both temperature and both pressure, temperature and pressure both are changing. Now for this change, considering the ideal gas behavior, we have to calculate the change in molar entropy. Okay. So now again we have to remind our formulas. Del S equals to NCV ln, so CVM ln V2 by V1 minus NR ln, oh, what am I writing? NR ln V2 by V1, or you can write N CPM ln T2 by T1 plus NR ln minus NR ln P2 by P1. I think the formula is correct. Or we can check it. How you can check it? Because you know for ideal gas, CPM equals to CPM minus CVM equals to R. This is for ideal gas. Okay, so now let me check whether it is correct or not, because there is a sign mismatch. I know It's better to remember, but currently I am not remembering. So let's say if it is correct, then we should check it whether it is the case. Then CVM can be written as N CPM minus R. Or anything still the call. Otherwise, the call will be disconnected. What is the specific? In RLM P2 by P1. Okay. And now for ideal gas, you know PV equals to NRT. N is fixed. Okay. So what? The PT should not be there. Oh, what have written? There was V, not P. Sorry. B2 by V1. Okay. So then also T2 V2 is not the case. So probably this sign will be plus. So if it is plus, then it will be minus T2 P1 and T1 P2. Then from here you can write T by V equals to P by NR. Therefore, it can be written in CPM ln P2 by T1 minus NR ln P2 by P1. Yes. Okay. So the formula should be here is plus. Here also. But here that did not matter because this part was anyway 0. Okay. So now we have to use this formula here. It's clear. So del S. What will be the CPM? Now we have to calculate CPM. For argon gas, you have already calculated for the last question. CPM was 3 by 2 R. So CPM will be 3 by 2 R plus R. It will be 5 by 2 R. So N into 5 by 2 R ln T2 by T1. What is T2 by T1? T2 T1. So it will be 200 by 300 minus NR ln P2 by P1. What is P2 by P1? P2 P1. So 10. And what is the N? N is 1 mole of gas. So we can ignore the N. So it will be anyway 5.5 by 2 R ln 2 by 3 minus R ln 10. So we have to calculate this. So now we have to calculate this. Let me calculate ln 2 by 3 into 5 by 2 means 2.5. So it is, if you common R, then it is minus 1.10136 minus ln 10. What will be the ln 10? Should be 2.3025. This is ln 10. So it will be something into R. And what is the R? R is 8.314 in joule, obviously, and it is 3 point. So it is minus 27.57 joule per joule mole inverse Kelvin inverse. That is the unit. Okay. Probably okay, sorry. That should be now because this is unit of R. What is the R? R you know, PV by NT. PV is the force, that is joule. An is mole inverse and P is Kelvin inverse. Okay. Now this is our answer for question number 2. Now jumping to question number 3, because today we are going to basically solve various question. Okay. So question number 3. The maximum non-PV work this is not the pathetic. This is from disconnection. The non-PV maximum non-PV work. That a system can perform at constant pressure. So we have to identify the maximum non-PV work done that a system can perform at a constant pressure. Okay. So how can do? Let me start with the first law of thermodynamics, which is du equals to d cross q plus d cross w. Now d cross w is actually d cross w mechanical, which is actually the PV work, and d cross w non-mechanical, which is non-PV work. So we are interested in this quantity. Okay. So what you can write, d cross q plus d cross q mechanical, which is essentially the PdV minus PdV, and d cross w non-mechanical. This is our first law now. Okay. So now we have to find out now uh, maximum non-PV work we have to find out. Okay. So from here you can write because Q non-mechanical work is eventually du minus d cross q, which is d TdS plus PdV. This d cross q. Now from here it's clear that from this equation we have to find out the d cross q non-mechanical work when it will be the maximum. That thing we have to find out. Okay. So now how you can do that? Okay. You know, we know that BH is du plus PdV plus VdP. Okay. And dg is dh minus TdS minus SDT, that you know. So now from here at constant pressure process you have to, because all of these we are considering a constant pressure process. So for constant pressure process you can write dH at constant pressure is eventually du plus PdV. So you can write it. This is eventually dH minus TdS because we are considering the const constant pressure process only. Okay. So dH minus TdS. So it can be written as dH minus TdS is eventually dg plus SDT. Okay. So dg plus SDT. So this is our because to non-mechanical. And when it will be maximum? Obviously when dg is maximum. So from here, because this is a positive term, S plus dt. If we are considering, let's say if temperature is increasing, then it will be positive, otherwise it will be negative. Whatever it is, this sign is positive. From this statement, it was not uh, can't be stated because here it is negative sign, it's positive sign. So you can't say that. So what is the catch? You from here definitely you can say that non-mechanical is eventually greater than dg if dt is positive. For a change, if dt is positive, we are saying this is true. So that's why you can say that you can relate it with the change in Gibbs energy, BG. So it's a tricky question. So this is the actual form. So in general, you can say this is the highest non-mechanical work you can get, highest non-mechanical work without ignoring any term. Only we have applied that constant pressure restriction because that is already mentioned in the question. Okay. Now, if it is an isothermal process as well, now if it is an isothermal process also, then d cross q non-mechanical work will be essentially equals to dg. This equation is very important. So we can say it is Tp, constant pressure at temperature. Why it is important? Because this is the general case. So most common condition, you can say constant temperature and pressure. So that's why dg Tp will be equals to mechanical. I think it's clear now. Now, next question. That's why that DG is in that important much. Okay, again, a numerical question is there. Oh, the vendor was for okay. This is just manual case question. This question we can skip. Okay, let me go to another set of question. Yeah, 5 gram ice at 200 Kelvin is added to 30 gram water in thermally isolated. Oh, sorry. Isolated also correct word. But here this is written as insulated in the insulated container. What would be the final equilibrium temperature? What is given here? Given del H fusion is of ice, obviously of ice, at 200 Kelvin is equals to 300 joule per gram. And it is also given the average specific heat capacity of liquid water, that is also given, that is 4 joule Kelvin inverse gram inverse. So this type of question probably you have solved in your high secondary levels. Okay, so heat, amount of heat transferred, that can be calculated. Heat transferred, that can be calculated using this formula, which is M, that is the mass times, that is mass times our uh, specific heat. What is the specific heat? So specific heat is also given, but we have to use a perfect symbol or notation, whatever you want to say for that. In general, it is S, you can write specific heat, S into delta. So this is our formula. S is not entropy, that's why I was choosing a different notation. It's a small s, specific heat. That is the formula of heat transfer. Now here in the question, it should be, because this is specific heat. Specific heat means the change of heat, sorry, this is the specific heat capacity. That means uh, this is the amount of heat it actually occupied or transferred or released, whatever you want to say, per unit temperature change per unit mass. So when you multiply with the total number of mass and total temperature change, then obviously it will be the just measure of total heat transfer. So this is the case. Okay. Now here, what is the case? 5 gram of ice here. Water was there. That is our 30 gram of water. 30 gram of water is there at 300 Kelvin. And we are giving ice how many? That how much? 5 gram of ice, which is at obviously 200 Kelvin. So now we have to find out the total temperature. So here the heat Obviously, heat will be transferred from hotter body, more hotter body to colder body. So that means heat will be transferred by the water to the ice. So heat transferred from water, that must be equals to heat transferred to the ice. So just now we can write this is M of water, S of water, and del T. That should be the same. No, that should not be the same. I'm just saying. So the del T of the water, ice, ice, ice. Which we have to find out. Mass, directly. Okay. And we have to be at equilibrium. It will be converted to a equilibrium state. Obviously, it will be converted to a equilibrium state. Yes, for some time, it will be converted to equilibrium state where the temperature should be the same. Let's say it's a T. That is the question. We have to find out the equilibrium temperature. So eventually, what will be the TW? TW should be TW initial minus TW equilibrium. Clear? So it is given that is 300 Kelvin, and this is the quantity we have to find out. So you can write is 300 minus T Kelvin. And why have minus it? Because this is just the the temperature will be decreased because it is going from the water. Or in general, you can give a more. Yeah, that's not good. Okay. But for ice, that's why it's important. We have to reverse it because it will be gained by the ice. So temperature will be eventually increased. Okay. So this is T and this was 200 Kelvin. So these things were now known to us. So by knowing this, we can rewrite the equation. Then it will be MW. MW is known. MW is known that 30 gram of water. You know the specific heat capacity of liquid water, which is 4 joule per Kelvin per gram inverse. And the temperature is also known 300 minus T Kelvin. So this is our left hand side. This is totally known to us. What will be right hand side? It will be 5 gram. It is 5 gram, obviously. Uh, Now, here one catch is there that you have to also keep in mind. Okay, this formula is okay if there is no phase change. So this is the very interesting part here. This formula is correct. This is excellent formula, but you have to keep in mind that for this case, I should be in the form of ice and water should be in the form of water. There must not be any phase change. If there are phase change, then you have to add that latent heat. You know that you have to also consider in that case. So obviously, the temperature of ice is here 200 Kelvin, and the melting point of ice is 0 degree centigrade, which is 273 degree Kelvin. So maybe there is a phase change. You don't know that. So that is also important. Okay, so that is important. Uh, what will be the phase change? But how you can predict that whether there will be a phase change or not? That is also important. But in general, you have to consider the phase change. Let's say there is a phase change, but we are not. If there is no phase change, then that part will be always zero. But in general, we have to consider the phase change as well. So here we have to consider the phase change as well. Okay. Hmm. So first, when you just understand it, when you put ice, when you put ice in hot water, because water is always hotter than ice, that is 300 Kelvin here. Now, when you put it in this case, first, what will happen? The temperature of ice will be increased. Just imagine. Water will be water, and the temperature of water will be decreased because the heat is transferring from water. That is clear. But what will be the fate of the ice? That is important to understand here. First, the temperature of ice will be increased. Then ice will be changed to a water. Then that water will be the water. That temperature of that water will also be increased. So you have to consider like that. Okay. So first you have to consider that ice is getting that ice will be increased. The temperature of the ice will be increased. So let's say so because okay before that what we can uh, give the logic. Let's say ice is not changing its state. If that is the case, and then we have to find out what is the specific heat capacity of ice. What is the specific heat capacity of ice? I think it should be one. Oh, no, wait. That is 2.108 kilojoules per kilogram per Kelvin. Okay, so let me put it. And daily fusion is given here. That is also important. The question you see here, daily fusion is given. That means this is the heat required for converting ice to water. So from question you can predict that the water ice will be converted to water. So let's say first. So now we have to generalize the formula. So first, what will happen? First step will be it is ice of a 200 Kelvin. First, it was ice of 200 Kelvin. Then it will be converted to 273 Kelvin ice. Then it will be converted to 273 Kelvin water, and then it will be converted to mm, some temperature, and that temperature will be equal because ultimately the both temperature should be equal. That water and that temperature should be equal. Total heat should be given. Yes, ultimately. So it will be 273 plus some temperature. Sorry, up to T. You don't know, just T in Kelvin of. That is the total procedure. And now you know for this step what will be the aim is all same. So for this process, the Q will be aim, which is 5 gram. Now we have to find out the S of ice, and it is 73. This is Q1, let's say. This is Q2. What will be the Q2? Q2 is easy. Q2 is just the heat of fusion, which is the daily is given, that is 300 joule for 1 gram, and there is a 5 gram. So it is 1500 joule. It's clear. And this step, this is Q3, and this will be our 5 gram of water. And this is known that heat capacity of liquid water, that is 4, and it is P minus 273. Okay, so finally we can write that is the left hand side. This left hand side, this unit will be goes away eventually. So it is 120 into 300 minus T should be equals to sum of all these three. So what, okay, one thing left is SI. That is 208 in kilojoule. Kilojoule means, let's say it is now in joule per kg per Kelvin. So this for 1000 gram. So for 1 gram, again it will be just this and it is gram. So you can write it. So it will be now 5 into 2.108 into 73 plus 1500 plus 12 into t minus 273. So this is our final equation to solve. So you have to solve it. So this will be 36. Okay. And this will be, this is just calculating. We have to calculate 2.108 into 73. 69.42 plus 1500 plus 20t minus 5460. So eventually it will be 100t equals to 3600 plus 5460 minus 1500 minus 769.42. So from here t will be this is 67 point. Oh, sorry, this is 140. And goes that side, it will be 140. Oh, and this is 6. Sorry, plus 5460 minus 1500 minus 1069.2 and divided by 150. 279.93 Kelvin. So you see, the final temperature is greater than 273. So you have to consider that phase change. Otherwise, it will give a wrong. So how you can calculate, how can understand whether there will be a heat change or not? Because this value you know, this value you can calculate. This is the amount of heat required to convert that ice to uh, ice at the 0 degree centigrade to 73 degree centigrade. So that value here is 76.942 this joule. This amount of heat is required, and you see from this calculation, you can predict that obviously that much of heat is easily provided by that water. So essentially, the ice will be converted to the water. So this is our final T. Okay. So again, now my earphone is connected. Let me connect it. So now the next question. Okay, let me find another type of question because I'm trying to discuss variety type of question here. Oh, this question or not. This question are related to Clausius Clapeyron that will be discussed in the next lecture. What type of question should I discuss? This type of question already I have discussed. For the reaction, this is the reaction given, and for the reaction, the given things are delta G standard is minus 16 point, delta H standard we have to calculate or estimate delta G naught at 500 Kelvin if temperature. So this is the question. Okay, so we know the delta G for a certain temperature, delta G naught, and we have to find out for other temperature. That is the question. Okay, so how you can approach for that? You need the formula. Which formula? This delta G equals to delta H plus T into del of delta G divided by del. Gibbs-Helmholtz equation. There are two Gibbs-Helmholtz equation. This is one the Gibbs-Helmholtz equation. So, should I discuss this Gibbs-Helmholtz equation in details, or okay? Let me discuss it. Otherwise, it will be difficult to uh, understand. Okay, how this happens? This equation is required, you see, for this solving this type of question. But how we can derive this type of equation? So let me do. So you know Vg equal to Vdp minus SdT. This is known to you. So from here you can write del G del T at constant pressure, essentially the minus S. Clear? And you know G is defined as H minus Ts. So if G is H minus Ts, so from here you can write minus S eventually is G minus H by T. Okay. So now take a process for which you know that del G for a process, let's say A to B. This change you know the del G and you know the del H, everything you know. So when G is following this relation, so delta G will also following the relation. This happened, let's say you perform this change A to B a certain temperature T. Now you change the temperature G to T plus dt, and you are performing the same thing. So this time of del G will not be the same. This will be del G prime, let's say. Clear? So you can say when you change the temperature T to T plus dt, so the change will be also shift to this delta G to delta G prime. The change is also changing here. So it's there. So delta G to delta G prime. So you can write. So we have to find out. So we can write it as delta G plus delta of delta G. Just the same thing. You see, change is changed. Delta G is the change. That change is also changed due to change in temperature. Okay. So you can write it. So now we have to find out this thing. And and this is performed at a constant pressure. So this is important here. So how you can write it? You can write as, oh sorry, del G equals to, just follow this. So dg prime minus dg divided by del T at constant P. I think it's clear because we are just delta of delta d of delta G. This is the change in delta G. So there, that should be like this. So yes, from this equation you can say it. Hmm. Now, from here, if you calculate, see, is it delta, not d? It should be d, not delta. 1 minute. You forgot to join?
No, I was having my university practical exam. Sorry.
Oh, okay, okay. Then it's okay because I will anyway upload this in YouTube. Okay, just let me solve this question which I am discussing right now. Then I think next question, from next question you will follow. Okay, or other way, I'm just uh, summarizing this question, what I am discussing. I was solving this problem. You can see it. For this, we need this equation. This is the Gibbs-Helmholtz equation. So I was discussing the derivation of this Gibbs-Helmholtz equation. How we can uh, derive this equation? This is the Gibbs-Helmholtz equation, right? That's it. So how you can start that? Let's say you know dg equal to vdv minus sdt. So eventually from this equation you can write this is as minus s, and you know g is equal to h minus ts. So minus s will be g minus h by t. So this is the relation. Now how this you can understand, this is for changing g, but we know that in our thermodynamics we are always deal with the delta g. So delta g is important here. So let's consider a process A to B. This change occurred at a temperature T, and for this change, the change in Gibbs energy is delta G. But the same process, if you if you perform at another temperature T plus dt, then the change in Gibbs energy will be a different quantity. That is delta G prime. So you can write when it was T, the change in uh, Gibbs energy is delta G. And if you change the temperature from T to T plus dt, it is also changed to delta G to delta G prime. So delta G prime can be written as delta G plus change the D is the change, small change in the Gibbs energy change. So this is D of delta G. Now, if you interested to calculate that how this change is manipulated, this change is controlled by this dt. For that, you need this. And we are considering if it is a constant pressure process. So then from here you can, that I was saying that from here you can write it as delta, because delta and small del actually commute. So from here, if you follow from this equation, you can write it as delta G minus delta H. But what will be the T? Because T is not the fixed. T is also changing, but here we have to consider the initial temperature T. So that is delta G minus delta E by T. This you can relate from this equation. Okay, so that means from there you can write, so delta G is equals to delta H plus T into T at constant pressure. So this is our first Gibbs-Helmholtz equation, or form 1. This is one form of our Gibbs-Helmholtz equation. Okay, leave it. This is one form. There will be another form in terms of Helmholtz free energy. That's why it's called Gibbs-Helmholtz equation. This is in terms of Gibbs free energy, but same thing you can perform in terms of Helmholtz free energy. Okay, so let me do it, because that is not very uh, popular actually. The Gibbs form, the change in Gibbs free energy is very useful, but also there is a form of Helmholtz free energy in terms of Helmholtz free energy. So for that, you know that A is eventually U minus Ts. Same. From here you can write del A is del U minus T delta S. Also there should be a S delta T, but that we generally don't consider, because the temperature is, let's say there is very small change in temperature that we are considering, that's why. Eventually we should consider that S delta T is also there. Okay. So now if you following the same way, if we want to calculate this quantity, this quantity, so it will be, if you see from here, this will be change in the delta U, and this you have to take the derivative first and second. So from here you can see, or we can follow the procedure that we have already followed for here. Let's say it is for, instead of G we can do it for our very this case, for Helmholtz free energy. Let me do that. What is the general form of A? dA. A is U minus Ts. So dA is du minus Tds minus SDT. Okay. Just checking that OBS is going on. Okay. So here, from here it can be shown, it is okay. It's clear. Now here you see we consider the del A del T. Here also we'll consider. Before that, what is the du? Du is okay. If there is literature, it's okay. It's okay. Later you will take it from the YouTube. Okay, there is no problem. Okay. Okay. So how you can do it for the Helmholtz free energy? That is, you know that du is eventually TdS, that is d cross q minus PdV. So if you put it, so it is TdS is cancelled, so PdV minus SdT. So here also can write del A del T at constant volume is essentially minus P. Oh, sorry, minus S. Same thing. And you know the same thing, S is there, and S can be written as also, you know, here A is U minus Ts. So S is actually, minus S is actually U, A minus U by T, A minus U by T. Just instead of the Gibbs free energy, we are considering the Helmholtz free energy. So therefore, del P, constant P, eventually it will be delta A minus delta U by T, or therefore you can write equals to delta U plus T. So this is the same form you see for G and J. So if you write it up and down, so it was just delta H. Okay, so these are two equations. That's why it's called Gibbs modulation. So these two relations are very important. Now you can manipulate these two relations. So in general, you can write it del F, del E, del F, del T. Now, if it is Gibbs free energy, then it will be pressure. If it is Helmholtz free energy, then it will be volume. If it is Gibbs free energy, then it will be enthalpy. If it is Helmholtz free energy, then it will be internal energy. Okay, so these two are the main forms. So now, if you want to, if I want to solve this problem, so we have to here now we have to calculate the delta change in delta G. Okay, okay, okay. So let me start with this. So del of delta G by T, it's eventually equals to del G by T minus del H by T equals to, no, delta G will not, because delta G will not be there, sorry. Hmm. But then delta G is also in how we can approach. If this is the form, then how we can approach? Because here the important thing is we have to consider the delta, these things. You have to do this integration. But there is also a delta G. We have to consider that delta G as well. How we can do that? There is a way by which we can bypass this, but I don't like it. Okay, my Bluetooth headphone is again disconnected. No recording is going on. Now we have to calculate that changing delta G. Then GT square will be there, that things will be there. But I don't want that kind of forms actually. I have to solve this. Okay, let me try it. Be 1 minute. Okay. So this one is okay. So from here, what you can write? Let me do it. Let me let me try it. Okay. So de- del G equals to del H minus T del S. Okay. So if the temperature is constant, now until now the temperature is not constant. Temperature was varying, but the constant temperature process for that particular temperature, because here the temperature is changing from T to T plus dt. Correct. But at this temperature T, this is true for that particular temperature. For another particular temperature, for this temperature, this is true. This is T plus dt. This you know. There is no problem. For particular temperature, this is correct. So we are considering at that values for that temperature. That is this. Okay. So it is eventually del A by T minus delta S. Okay. So now if I want to differentiate it, then it will be del delta G by T by del T. This quantity at constant pressure. Then what will we get? So it will be, you can say this is first 1 by T is constant, and we are differentiating del G, del T at constant P, and then delta G is constant, and we are differentiating del 1 by T of del T at constant P. Correct? So that means the first part is known to us. This is the Gibbs-Helmholtz equation, this. So that is essentially del G minus del H. Okay, but the second part, that is del G, and this is del T of 1 by T. So it is minus 1 by T square. So it is minus del G by T square. So minus del G by T square. Here I am not using this formula anymore. I'm just, I'm trying from this equation. I don't know whether I will be, it will be correct or not. I don't know. That just I'm doing. Okay. So this, so from here, what we can write, del G, again, del G equals to del H minus C delta S. You know this. So if you put it, so del G, this is again T delta S will be there. What will be the case? And del S by T square is totally mess. No, that's okay. That's okay. I think I have done a wrong here because del G is there, 1 by T is there. So I think correct. Del G by T square is also going to be minus 1, minus 2. It's correct. It's correct. And from this equation, 1 by T. Here 1 by T is there. And the formula is saying this. This is, sorry, that's right. Here will be T square. Then it is minus del H by T square. And so this is the formula. So del of delta G by T at dt at constant P equals to minus del H by T square. So eventually you can write it, then delta G by T equals to, obviously at constant pressure, you can write it at dt. Now if you integrate it, then it will be delta G by T, and it is, let's say, from T to T plus T to another temperature T plus delta T. You don't know the temperature. So delta H is independent, that is mentioned is the in the question, and we have to integrate it dt by t square. So what will be the dt by t square? The dt by t square is eventually okay. When you are integrating this, so it is actually delta g by t, so it is t prime, so it will be delta g prime by t prime. So let me write it explicitly, otherwise it will be mistaken. Correct? So this is the case. Okay. So it will be minus 2, so it will be 2 by t cube t to t prime. So eventually t prime cube 1 by t prime cube minus 1 by t cube. So this is the answer. This is the thing that is required. So delta H is constant. So delta H we know. So we have what we have now in the question. Delta H is known to us. So delta H is given minus 46.11 kilojoule mole per mole. Okay. And delta G by T. Delta G at 298 Kelvin, it is given. Everything is not that, not means that for a particular pressure, that is 1 atm, and everything is for a constant pressure, that should not be 1 atm, but if it is 1 atm, then we have to put a not everywhere, so that we can ignore for right now. So delta G is given as minus 16.45 kilojoule per mole. So therefore delta G by T, that will be minus 16.45 by 298. So that is clear. So T is 298 and T prime is also asked, that is 500 Kelvin. Just put it. So delta G prime by 500 Kelvin minus, it will be plus 16.45 by 298 equals to minus sign is no minus sign 2 delta H. So 2 delta H will be 2 into minus 46 point. So now there will be minus 1 into 1 by 500 cube minus 1 by 298 cube. So we have to solve it. Then we can obtain that delta G prime. That is the important things. That was the thing asked in the question. Okay, so it will be now this part. Okay, 1 by 500 cube. We need calculator. 1 by 500 cube minus 1 by 298 cube. This is very, very small quantity, obviously. Cube is there, t to the power cube is there. So eventually it is given as minus is there. So my 2 into 46.11 into 3 into 10 to the power minus 8. So it's very small quantity, you can see. But this is kilojoule. So there will be a 10 to the power 3. And this is also in terms of kilojoule. So it will be again 10 to the power 3. I'm not wrong. I think it's correct. If there is any mistake, correct me in the next class. I don't know. I'm just trying to solve this type of question because this is not very regular type of straightforward question. Okay, you can see here. Cube is anyway From where this is. But if we started with this formula, then what will be the problem? Yeah, so we can solve. Let's see. Just try. Because this is not the correct answer. Because you can see here 10 to the power minus 8 is there. So forget it. So if it is, let's say, let me try it once. Otherwise, I figure it out and I will discuss it in the next class. Okay. So let me, if I started with this formula, delta G equals to delta H plus T into delta G delta T. If we start with this one, then obviously it will be, but delta GT will be there, and we don't know how that delta G depends on that temperature. For that, again, we need to invoke that. There is the problem, no? There is the problem. I don't think this is a wrong, but this minus 8 is okay. For time being, let me, I will figure it out and I will discuss it in the next class. Okay. Without wasting our time, because we have to discuss lots of question. So the next question is, what is the delta G naught for the reaction? C graphite plus 2H2, which is in gaseous form, N2, which is also in gaseous form, okay, plus half O2 is converting to CO, NH2, whole 2. For the, we have to find out, and what is the given? Lots of things are given. This is given CO, this reaction is given, for which delta G naught is 1.91 in terms of kilojoule per moles. Second reaction is also given, which is H2O in gaseous state to H2 in gas plus half of O2. 227.44. Here it is minus 394.38. This is, so from these four data, we have to find out the del H for this. You know del G, sorry. Del G is a state function. So eventually you can add up. From these four reaction, we have to make the final one, for which we have to calculate the del G, that is this. So in right hand side, this is the test. So this is 1, 2, 3, and 4. If we add, this should be left hand side and this should be right hand side. It is clear. So clearly we have to add 1 and 3 first. It is clear. 1 and 3 have to add. Then CO2 will be there. CO2 will cancel out. Okay. O2 is there. There is also O2. Ammonia is there. Ammonia will be cancelled out. N2. pH. Okay, we have to just add all four, I think. If we add, then obviously in left hand side it will be CO2 plus 23 plus H2O plus C graphite plus O2 plus N2 plus 3H2. And at right hand side it will be H2O CONH2 whole 2 CO2 gas CO2 2NH3 plus H2 half. So now if CO2 will not be here, ammonia will goes away. It will be equals to C graphite plus N2 plus 2H2. H2O will not be there. Okay, O2. Okay, so this is, and we need also this. Okay, so obviously the final del G will be del G 1 naught. Here it is straightforward, but if it is not, then we have to multiply in some factor, then we have to add it. That we have to figure it out in that case, obviously. So if we add it, so it will be 1.91 this kilojoule per, and it will be minus 197.46. Okay, so this will be the answer. Oh, so now next question. Next question is, for an ideal gas, undergoing isothermal reversible expansion, okay, then delta G is equals to, there are four options, delta U equals to delta U, delta S, delta A, or delta T. Okay, so what is our DG? VDP minus SDT. Now it's isothermal, so this will not be there. So it is essentially our, so DG will be VDP, ideal gas. So delta G will be nRT by PdP. So it will be nRT ln P2 by P1. So we have to find out among these property which will be the equal to this. Isothermal means delta will be 0. So we can ignore this option. That should not be. Now other four option, DU. DU is, TDS minus PdV. Okay. Correct. And you know that delta G is equals to delta H minus T delta S eventually. And delta H is equals to delta U plus P delta V plus V delta P. So eventually it's clear that these two properties not equal to each other. Purely not delta S. Let me check the delta A because both are heat energy, right? Free energy. So it may be. So delta A was delta U minus TDS minus SDT. So, and why the reversible process is mentioned here? Because you know this all equals to signs are there. That's because of the reversibility. Okay. Now du is eventually TDS minus PdV minus TDS minus SDT. So it is minus PdV SDT, and at a constant temperature it will be 0. So it is essentially minus PdV. So A will be delta A will be minus PdV. So it is nR P is nRT by V nRT ln V1 by V2. Okay. So this is isothermal process. Okay. Isothermal process is there. That means Pv are changing. That means P1 V1 equals to P2 V2 from the Boyle's law. Follow this should be followed by ideal gas because this is isothermal process. So here nRT will be ln P1 by V2 equal to P2 by P1. So it is essentially equals to the delta. The correct option should be our delta A. Okay, so this is our question number 7. Now the question number 8. Okay. Oh no, 6 it was, sorry. It's question number 7. Let me again find out some different type of question. These questions are good. Mhm. Here lots of miscellaneous questions are there, but let me just show that the change of 2 mole, what is the change 2 mole of an ideal gas which was at 2 bar 273 Kelvin to 2 mole of same gas 1 bar 273 Kelvin. The temperature is fixed, you see, we are changing the gas. Carried out irreversibly against an external pressure of 1 bar. That's already seen, spontaneous. So we have to show that this change is spontaneous if you are considering a irreversible process. So you know, for irreversible process, if it is a equilibrium reversible process, then that is dG equal to vdv minus STT. Okay, and we have already derived the conditions for spontaneity that this should be the negative. So it is actually the negative. The negative is for equilibrium, for irreversible process. Okay, so we have to show that that should be, now you look, there is no dt, so just only vdp is there because it's the isothermal process, temperature is same, vdp, and it is ideal gas, so vdp can be written as, okay, let me write it. Then it will be nRT ln p2 by p1. So nRT ln p2 by p1, so p2 by p1 is half, so it is actually minus 2. N is also 2, 2RT ln 2, so minus 2RT ln 2. So if I write it like this, so clearly it's seen that the delta G is eventually negative. So if delta G is negative, that means it's a spontaneous process. That's it. Straightforward question. In this way, you can prove it. Okay. Yes. The delta. No. DG equal to BDP. That's correct. That is no problem. Mm, What is what was our the definition of spontaneity? That is important. There was a negative less than zero. It should be less than zero. That should be the case. DG equal to BDP. That's true. Let me again remind. From where it appears, everything. Du equals to d cross q plus d cross w, right? So it's eventually pdv minus pdv for non-mechanical, for mechanical work. Now for reversible process, d cross q is tds, but for irreversible process, d cross q reversible is less than d cross q reversible, so it's less than tds. So for irreversible process, this TDS minus PdV for irreversible process. And for reversible process, it's equal. So now if you put it, then dH would be equals to dH, dH is, these relations are true. So if you put it, then it will be TDS minus plus VDP. Correct? So dG, that was equals to dH plus, not plus, minus TDS minus SDT. So again, if you put it, then we'll obtain VDP minus SDT. So this lesson actually the equal to, for equal sign signifies the spontaneous process, reversible process, and the negative sign is for irreversible process. That's okay. For the if the state is changing from, let's say, A to B, then this is the case. So when it's a constant pressure and constant temperature process, it must be, dg must be less equals to 0, like that. From here, if it is equals to 0, that means it's the equilibrium process. If it is a less than 0, it's a irreversible process. That means it's a spontaneous process. And here you can see it's a negative value. How? Because irreversible, it's said, so there will be negative sign. So it's a negative sign. So it's obviously a less than 0 quantity. So it's a reversible process. Okay. That does not mean, if it is a positive term, then you can't say whether it's spontaneous or not. Okay, now the next question. Sorry. This is viscosity question. Let me don't discuss it. Okay. Oh, it's a great. What is a delta A for the process? What is the process? 2 mole of helium against gas 5 atm. Assuming, okay. So you have to calculate that delta A. So dA was du is TdS minus. Okay. And here temperature is fixed, you see. So it will be minus PdV. So delta A will be, you have to consider the ideal gas anyway. So it will be minus nRT ln V2 by V1. Okay, that's the answer. And now we have to find out what is the V2 and V1. That is not given here. The pressure, and so you know that P1 equals to P2 V2 for the Boyle's law. Boyle's law will be valid. It's isothermal process. That's why. So you can write it as P2 by P1, and you can note that minus sign. Then the minus sign will be captured there. So it will be 2 moles. So 2 RT ln P2 by P1 5. P2 by P1 is 5. So 2 RT ln 5. So 2 8.314. What is the temperature? Temperature is 300 Kelvin and ln 5. And unit, it has no unit. It's actually joule per Kelvin per mole. It's actually mole, joule per Kelvin per mole, Kelvin. So eventually it will be joule. So now we have to just calculate it. What will be the value? It is 2 into, okay. So this is our change in Helmholtz free match. Next question, it was question number 8. Now question number 9. Okay, so now question number 9. Okay, what is the question? The delta S for 3 mole of an ideal gas which is diatomic, okay, that is which is heated and compressed from 298 Kelvin and 1 bar to 398 Kelvin and 5 bar. So same type of question that is given, Cp is given. So it is easy, I think. So here we will use the formula that del S, that was nr ln T2 by T1, sorry, n Cvm ln T2 by T1 plus nr ln V2 by V1, but here the pressure is also changing, so we'll use P2 by P1 obviously, then it will be minus and it will be Cpm, I think. Yeah, because this already we have done before, so this we can check what was our, yes, there, yes, perfect. Okay, so now it's easy, we have to just calculate it. 3 mole and Cp is given. This is basically Cp for 1 mole, that means it's actually Cpm. So 3 into 7 by 2 R ln 398 divided by 298 minus 3R ln 5 by 1. Okay, so now if you calculate, so it will be eventually, if 3R, okay, first this value ln, let me calculate, ln 398 divided by 298, so it is 0.289, so it will be 3 into 3.5 into 0.289 minus 3 into ln 5 and overall R. And what is ln 5? ln 5 is 1.609. Okay, so just let me calculate it. So it is 3 into 3.5 into 0.289 minus 3 into 1.609. Okay, so eventually it becomes minus 1.7925 R. So in joule it is 8.314 joule per Kelvin. Okay, so it is 14.90 joule per Kelvin. Okay, so it's just straightforward question, but this type of question is frequently asked in the okay. So now going to the next question. It will be now question number 10. The molar heat capacity at constant pressure, that means Cp of H2 gas, that constant pressure is 1 atm, that is given by, with this equation, which is Cp equals to 30.54 plus 10.3 into 10 to the power minus 3t. This is Cp. Now they asked the change in entropy when 2 mole of water at the same pressure 180 m at the temperature that is changing, that is increased from 300 Kelvin to 1000 Kelvin. Now we have to measure it. Okay, so here it's clear that temperature is being changed and it is the H2O gas, and it is 300 Kelvin gas. Okay, let's change it 400 Kelvin to 1000 Kelvin. Okay, so now what will be our formula? We know that ds eventually is TDS is actually d cross q. Okay, and we know du is d cross q minus PdV, considering only the mechanical work. Then d cross q will be, even so you can write it, d cross q is du plus PdV. Okay, and du is eventually CVdt. So now what we can write it here, so ds is eventually Cv dt by t plus p by TdV. Considering ideal gas, nRT equals to PV. So P by T is nR by V. So it is nR by V. Now we have to integrate it. Okay. So if we integrate, then we can calculate. But here Cv is not given, Cp is given, and for ideal gas, here ideal gas is not mentioned, but eventually we can consider this water vapor as ideal gas. Otherwise we can't use any equation. So for ideal gas, you know, Cv is eventually Cp minus nR, and how many mole is there? 2 mole. That we can change later. So it will be ds, and Cp will be Cp minus nR dt by t plus nR dv by v. So it will be delta s Cp dt by t minus nR ln t2 by t1 plus nR ln v2 by v1. So if we combine, then it will be t1 by t2 if we change the sign, and after combining we will obtain this. Okay, and pressure is constant, everything is happening at a constant pressure. So if pressure is constant, so you can write P equals to nRT by V. That means if pressure is constant, then T by V eventually will be P by nR. That is also constant because n is 2, R is universal gas constant, and pressure is also constant. So T by V will also be constant. So you can write it T1 V1 equals to T2 V2, or you can write T1 V2 by T2 V1 equals to 1. So if you put it here, so it will be ln1 and it will give the 0. So this term disappears. So we will obtain Cp dt by t integrating from T1 to T2. Now the expression of Cp that is given in the question, that we will insert here, that will be 30.54 plus 10.3 into 10 to the power minus 3 times t into dt by t. So if we simplify it, then we will obtain T1 to T2. It will be 30.54 dt by t plus 10.3 into 10 to the power minus 3, again integrating t1 to t2, and here it will be only dt. So eventually the answer will be 30.54 ln t2 by t1 plus 10.3 into 10 to the power minus 3 del t. So what is the del t? Because t2 is given here as 1000 and t1 is 400. So t2 is okay. In no r has n is not important here. Yes, n will not be eventually important. But what is the cp? That cp is for this is molar heat capacity. Okay, so this value we have written, this is the molar heat capacity, so it's basically the cpm. So for that you have to multiply it with n as well. Okay, so n will be there and n is 2 for 2 mole, so everything is multiplied by 2, so it will be okay. So t2 is 1000 and t1 is 400. If that is the case, so it will be 30.54 into 2 is 61.08 ln 5 by 2. If you use these two values, then it will be 5 by 2 plus 20.6 into 10 to the power minus 3 into 600. Okay, so eventually it will be 600 by 1000. So 6 by 10 means 3 by 5. So it will be in ln 5 by 2, and this gives us 55.967 plus these things, right? So it will 20.6 into 3 by 5, so it is 12.36. So now if we add both, then it obtained 68.327. and what will be the unit? The total unit will be joule per Kelvin. Okay, so because the cp is a unit of joule per Kelvin, that from that unit, so it will be joule per Kelvin. So this will be our answer. Okay, 68.327. okay. Okay, so we can discuss any other question. This mixing type of question we'll discuss in the next class, that delta T mix, delta H mix, delta V mix, delta X mix for ideal gases, or if it is not ideal gas, then what will be the answer? That we will discuss in the next class. For timing we can stop here and we will meet again in the next class. So as today no one joined effectively in this class live session, so eventually I will upload this total course, total class. I am being recording. I have recorded total class and I will upload in the YouTube, and I will share that link as well in the spreadsheet, so you can follow. And if there is any doubt from this question, you can ask me in the next class. Obviously there was a doubt in that question. That question I will surely discuss in the next class. No, not that one. This question, I think, yes, this question was not completed. I will discuss in this question in the next class surely. I will resolve this doubt, and in next class the phase question from phase equilibrium also being addressed. So for today we can stop here, and as no one has joined, so I can directly leave. And so please gone through the lecture which will be uploaded in the next week, that means in this week, that if there is any doubt from that lectures or this lecture I have discussed, I will upload that on YouTube. Then, or if there is any other doubt, you can ask me in the next class. Okay, and that gives Helmholtz energy, that question also be, I'll clear that question as well. Okay, so thank you for listening. Okay, we'll meet again next Sunday from 4 to 6. Okay, so thank you all.